Assalamualaikum and good day. So we will start with the first learning unit, which is Chemical Kinetics Part 1. So these are the learning objectives that everyone must be able to accomplish. The first one is to define rate of reaction. Secondly, identify types of reaction. Thirdly, explaining factors which affect reaction rates. Fourthly, expressing the rate law, followed by solving problems associated with rate constant. Next is distinguish between molecularity and order of reaction. And then finally, last three, plot of zero order, first order, second order, and third order. So let us look at what kinetic is. Okay, so kinetic is actually study of speed, okay, in which chemical and physical processes take place. So we are focusing on kinetics for chemistry. Okay, so when we talk about chemical kinetics, we are trying to answer the question of at what rate, okay, what rate does a chemical reaction undergo change under a given set of condition. A given set of condition means what is the concentration of the solution, what is the temperature. So those are the set of condition. So when you have this set of condition, what is the rate of chemical reaction? Okay, if the concentration is high, temperature is high, does the rate of chemical reaction fast or slow? Okay. Secondly, what effect will a change in condition will have on the rate at which a chemical change occur? Okay, like I mentioned just now, concentration of solution, for example. Okay, so at low or dilute concentration, what would the effect be? At high concentration, what would the effect be? Okay, to the speed of reaction means the time for the product to form, for example. Okay, and then the last question is what information is available as to how the chemical reaction occurs. Okay, first let us look at types of reactions. So generally there are two type of chemical reaction. Okay, either it's homogeneous or heterogeneous. Okay, homogeneous mean the reaction occur in only one phase. Okay, and the system is uniform throughout. So if you look at the example here, okay, when we have hydrogen react with iodine forming hydrogen iodide, so all are in the gas state. So that's what it means by homogeneous. Similarly, the second reaction here, okay, liquid, all in liquid state. Okay, okay. Next is heterogeneous. Okay, so heterogeneous is reaction that occur on the surface of a catalyst or the wall of a container. Okay, and the mixture is not uniform. Okay, not uniform means you have other state of matter besides that one phase. For example, this reaction here. Okay, the first reaction is ammonia on the surface of a tungsten to form nitrogen and hydrogen gas. Okay, so you see here, these are all in gas phase, but the reaction occur on the solid surface of a tungsten. Okay, similarly, ethanol here. Okay, ethanol is in liquid form. Okay, on the surface of alumina forming forming ethylene and also liquid water. Okay, ethylene gas and liquid water. Next, we look at the two types of reaction rate. Just now, two types of reaction. Now, two types of reaction rates. Okay, the first one is instantaneous rate. Second one is average rate. So what does it mean by instantaneous rates? So this means it's the change in the product formation at a moment in time. At a moment in time means when you look at the graph at one particular time. What is the instantaneous rate? So that's what it means by instantaneous rate. Okay. So to get this instantaneous rate, we have to draw a tangent slope, okay, which will give us the instantaneous rate at that particular time. Okay. Average rate. Okay, average rate is the difference in the concentration of product or reactant divided by the difference in time. So this average. I'm sure you know what average is. Okay. Product final concentration minus initial concentration of the product, okay, divide with the time where the final product form minus time where the initial uh, uh, initial of the product. Okay, so that is average rate. To understand this better, let us look at this plot here. Okay, so this plot here, okay, for concentration, okay, change in the concentration versus time. Okay, so we will always get a curve plot like this. Okay, so this is the plot of a reactant, means the reactant concentration decreases over time as the product form. Okay, so when we plot product, it increases in concentration over time. Okay, instantaneous rate is at moment in time. For example, we want to find what is the reactant at this point of time here. Okay, at this point of time. So that's why we have to draw this tangent slope. Okay, from this tangent slope, we can find the instantaneous rate. Okay, okay, concentration of final minus initial divide with the time here. Okay, final and initial. Okay, to understand better what is instantaneous rate or average rate, you imagine you are driving a car. Okay, you are driving a car, and you look at your speedometer. Okay, your speedometer will show you your instantaneous rate at the point when you look at your speedometer. For example, you are driving, and the moment you look at the speedometer, that is your instantaneous rate or instantaneous speed. Okay, sorry, instantaneous speed. Okay, let's say 50 kilometer per hour. When you calculate the average, okay, you have to consider the time taken from the uh, of your travel time, okay, before you travel, and the time when you reach your destination. Okay, and then your average speed is the range of um, uh, the initial speed before you start your journey, and then at the end of your journey. Okay, so that is your average uh, speed. Okay, so means when you're constantly driving 60 kilometer per hour, and then um, you will reach 60 kilometer in 1 hour of journey. Okay, so that's what it means by average. Okay, now next we look at rate of reaction. Okay, so rate of reaction is defined as the number of molecule of a given species reacting per unit of time and this will show how the concentration of the reactant or the product change over time. Okay, now let us look at this example here. Carbon monoxide reacting with nitrogen dioxide at high temperature of 200 degrees Celsius, forming carbon dioxide and also nitrogen oxide. Okay, so to express this in terms of the change in concentration, this is how we write the rate. Okay, rate is negative d, okay, square bracket of the reactant over dt. Okay, so when you look at reactant, so these two are the reactant, so that's why you see negative carbon monoxide over dt equal with also negative d concentration of nitrogen dioxide over dt. Okay, and this minus sign here makes the rate a positive quantity. Okay, so it becomes a positive quantity because the initial and final here. Okay, so it become if you look back at the slope just now for reactant, it's like this, right? So initial is lower than the final, so it become negative value. So negative will, with negative sign, will give it a positive quantity. Now when we express in terms of change in the concentration of product, it become a positive value. Okay, here, because go back to the plot just now, product increase over time, so it become a positive value. Okay, the final minus initial will give you a positive value. Okay, so just now product is carbon dioxide and also nitrogen oxide. Okay, so you express it in terms of rate, positive value of D, concentration of carbon monoxide over dt, also equivalent to positive D, concentration of nitrogen oxide over dt. Now look at this jar here. Okay, so this jar is showing in terms of the number of molecule when a reaction takes place. Okay, so in the beginning, okay, 0 second here, we have 1 mole of reactant A and no product form yet. Okay, so over the time, okay, 20 seconds, some of the reactant A has been converted to product B. So basically we write the reaction like this. Okay, so note that the amount of the number of mole of A decrease is similar or same as the amount of product B form. You see here, okay, initially 1 mole, okay, it reduced to 0.5454, means 0.46 has been used to convert to product B. Okay, and then another 20 seconds, more of reactant A has been converted into product B, and it still gives you a total of 1 mole. You see the amount, okay, amount of reactant, okay, decrease is the same of amount of product form, and we can calculate rate here. Remember, the rate is, okay, negative D concentration of the reactant A over dt. Okay, or if you look at B, it's positive D B over dt. So T here is referring to this, okay, time here, second. Okay, so let us look at this reaction here. Okay, A plus 2B forming 3C plus D. So based on this balanced chemical reaction, okay, B is consumed twice as fast as A, because you need twice amount of B to react with A in order to form 3 times fast of C compared to D. Okay, so when you see there's a stoichiometric value here, okay, you write it in terms of fraction in the rate of reaction expression. Okay, here. Okay, so because D and C are products, so it's a positive value. Okay, here. Okay, and then C is 3 mole, so write in the fraction of fraction 1 over 3. B is the reactant, so it's negative value, so because 2, stoichiometrically 2 value here, so become fraction negative half. Okay, so let us look at this example here. Okay, hydrogen iodide gas forming hydrogen and iodine gas. Okay, so the rate of consumption of hydrogen iodide is double. Okay, the rate of formation of hydrogen and also iodine. Okay, so we write the rate of reaction. Okay, this is how we write the expression. Okay, half negative half d hydrogen iodide here over dt equal to d hydrogen over dt and d iodine over dt. Okay, because these are the products, so it's a positive value. Okay, not that equal sign. Okay, okay, this is the same. Okay, so you have nitrogen and hydrogen forming ammonia. So product, you see a negative sign, a positive sign, sorry, positive sign. Okay, because stoichiometric 2 value here becomes fraction 1 over 2. Okay, these two are reactant, so it become negative sign here, and if you have stoichiometric value, it become a fraction here. Okay, now let us look at example involving calculation. Okay, so the rate of consumption of methyl radicals in the reaction of methyl forming ethane, okay, reported as 1.2 mole per liter per second under a certain set of conditions. So the question is, what is the rate of the formation of ethane gas here? Okay, so what is the rate? Okay, remember rate, you must have value. Okay, um, concentration over time. Okay, so given the rate is, okay, so rate, so this is actually referring to rate. Okay, rate, because it's referring to product, so it's a positive value, no stoichiometric value. Okay, so this is ethane, CH3CH3. Okay, so this is dt. Okay, so the value is given. Okay, 1.2, okay, mole per liter per second. Okay, so the question is, what is the rate of formation? Formation, this. Okay, so there is 1 mole of ethane formed for every 2 mole of methyl radical consumed. So that means the rate of formation of ethane is half the rate of consumption of the methyl radical. Okay, you see here, this value is referring to the rate of consumption of methyl radical. So this is referring to, okay, okay, 1 over 2. So we can also write in the rate here equal to 1 over 2. Hang on, let me just cancel this. Okay, so we put we write it again. So rate here equivalent to negative 1 over 2 d ch3 over dt, right? Also equivalent to positive d ch3 then ch3 over dt, and this value are 1.2 molar per liter per second, and this value is referring to the rate of the consumption of this. So because this is having this value here, remember, so therefore this is also half. Okay, so that's why the value of formation of the ethane is 0.6 mole per liter per second. Okay, so I write is molar here. Molar is referring to mole per liter. Okay, next we move on to factor affecting reaction rates. So there are 5 factors affecting reaction rate. The first one is the nature of the reactant itself. Secondly, the surface area of the reactant. Thirdly, the concentration of the reactants. Fourthly, temperature, and last is nature of the catalyst if catalyst is present in the reaction. Okay, now let us look at the first one. Okay, first we look at the first factor, which is the nature of reactants. So if we look at the first example here, chemical reaction between silver ion and also chloride ion forming silver chloride solid. Okay, these are example of ionic reaction. Okay, so these reactions are very rapid, okay. However, if the reaction involving electron transfer, for example here is iron 2 plus with cerium 4 plus forming cerium 3 plus and iron 3 plus, this is longer compared to the ionic reaction. Okay, another reaction is complex reaction. Okay, for example, reaction between magnesium 2 plus ion and also oxalate 2 minus forming magnesium oxalate solid. So this reaction is slow in nature. Okay, so the nature of the reactant will will um, will affect the rate of the reaction. Okay, next we look at the second factor, which is surface area of the reactant. So in heterogeneous reaction means it involves solid surface for reaction to occur. It will the rate of the reaction will depend on the area of contact between the phases. Okay, so the rate of reaction will be proportional to the surface area. So if the particle size of the reactant is low, okay, is small, okay, then the surface area is high. Okay, if we go back to the previous reaction that involved the surface of tungsten, for example. So if the surface area of the tungsten is high, so the tungsten is big in size, okay, and um, the particle size of the reactant is small, then the reaction of the rate of reaction will be high. Okay, because it's the rate of reaction is proportional to the surface area. Surface area low, then the rate of reaction also low. Next is the third factor, which is concentration of the reactant. So higher concentration of reactant means increase in term of the rate of reaction. So if we have this reaction here, A, reactant A forming product, the rate will be double if the concentration of the A is double. Okay, so concentration of reactant increase means molecularly number of particle per volume will be high, and this will lead to effective collision rate because of the molecule, okay, and leads to higher rate of reaction because increase in concentration, number of particle higher, number of particle high, so more will attack the volume area, given volume area. So that's why the collision will be higher. Higher collision, higher rate of reaction. Okay. So this is reaction here, figure and the plot here showing the effect of concentration to the rate of reaction. So we have solid magnesium. We drop it in the tube filled with hydrochloric acid, okay, aqueous form. So this will leads to the formation of magnesium chloride, okay, which will dissolve in the magnesium solid, will dissolve in the acid, okay, and at the same time releasing hydrogen gas. So here is two different test tube with different concentration of acid. So here is 0.3 molar, here is 6 molar, so this is higher, okay, much higher compared to this. So in which test tube would the magnesium dissolve faster? Of course, in the higher concentration. Okay, and to calculate the rate, let us plot. Okay, in terms of the mass of the magnesium versus the time it disappear. Okay, initially there's 0.55 milligram of magnesium, okay, in both test tube. Okay, over time, after 100 seconds, okay, the amount of magnesium in the 0.3 molar okay, reduced to this much, okay, and then after 200 second here, after 300 second here, after 400 second completely dissolve. However, in the 6 molar test tube, not even 100 second, the amount of 0.55 milligram completely disappear. Means the rate of reaction for this test tube is very much faster compared to this test tube here. Okay, so you can see the effect of concentration to the rate of reaction. Okay. Okay, so to find the value of the rate, of course, 0 minus 0.55. Okay, final mass minus initial mass over time here. Okay, so that is for 6 molar test tube. This is for 0.3 molar test tube. Okay, so 0.0 initially 0.55, okay, minus final mass is 0, initial mass is 0.55. Okay, so mass over time 400 minus 0, so from there you can calculate the rate. Okay, rate. Okay. Okay, this set here is showing the relationship between the rate and also concentration of reactant. Okay, so there's a 6 set of experiment here. Okay, there are 6 set of experiment. in which is each set will have different concentration of ammonium ion and nitrate ion. Okay, so if we compare experiment 1 and 2, okay, let us look at experiment 1 and 2 here. Okay, 1 and 2. Okay, experiment set 1 and set 2 will have the same concentration of nitrogen dioxide, nitrate ion, whereas the concentration of ammonium ion different. Okay, set 2 double compared to set 1. So let us look at the rate. Okay, the rate become almost double also. Okay, so next we compare experiment 5 and 6. Let us look at experiment 5 and 6, in which the concentration of ammonium ion now is the same, but we change the concentration of nitrate ion. Okay, we double. Okay, look at the rate. The rate also considered double here. Okay,